Alright, so begins lecture 18 on adapted frame fields and connection forms on M. We're in chapter 6, and so let's just get to it. Basically the idea is we want to use frame fields and the connection form formalism we talked about back in chapter 2 in such a way that it naturally picks up on the geometry of surfaces in R3. So the natural starting point there is to talk about what's called an adapted frame field. So an adapted frame field, oh sorry, I'm showing you all my theorems. Oh no, all right there. An adapted frame field, well, what is it? It's a frame field, all right, such that the third, E1, E2, E3, such that the third frame field is normal, all right. So basically E3 is the U we've been talking about before. Although it doesn't have to be the case that E3 appears as the XU cross XV or something like that. I mean, there's no patch here specifically. We're working directly with the frame field as opposed to working with a patch or an equation. Although, of course, for a given example, you can always go back to patches or equations, like chapter 5. All right, now, so of course we assume orthonormality. All right, it's an orthonormal frame. And, of course, the first two, E1 and E2, have to be in the tangent space, right? And as O'Neill tells us, you can talk about it for some subset of M, but often we just say it's a frame field on M with the understanding that, hey, it may not cover all of M, so it's kind of cavalier, but not too harmful really. Like, for example, we'll talk about a frame field on the sphere, but technically speaking, it's on the sphere modulo the north and south pole, right? Typical abuse of language. So here's lemma 1.2. There is an adapted frame field, if and only if the set is orientable, and there exists a non-vanishing tangent vector field on the set. So the forward implication, suppose you got an adapted frame field. Well, then basically E3 is your unit normal, and so it's orientable, all right? On the other hand, E1 or E2 serves as a non-vanishing tangent vector field, so there you go, there's the forward implication. On the other hand, going backwards, this is where the calculation, the proof at the moment actually, gets at least a little bit interesting. Suppose that, oh yeah, there we go. Suppose theta is orientable. I mean, the set is orientable. The script O, I suppose, it's not actually a theta. Mine look like theta, but it's actually some kind of like, oh, I don't even, anyway. You see the symbol a lot as you read higher math, so you probably should figure out what the name of the thing is. Anyway, it's on my list of things to do. But let's just call it O. O is orientable. That implies that there is a unit normal on O, and so we can take E3 to be that unit normal. All right, so there's one down, two more to go. We're also going to assume that, of course, there exists a non-vanishing tangent vector field on O, and, well, we're going to call that E2, all right, because we can call it that. And if E2 wasn't normalized, I should say, normalize it, all right, so that way we've got two unit normals, two unit vector fields, one of which is normal, the other which is tangent. And then how do you get a third thing, which is perpendicular to both of these? Well, you cross product, right? That's what to do. We're in 3 dimensions, so we take E1, we use E2 cross E3, and that gives us a third vector field for which E1, E2, E3 forms a frame. In fact, it forms a right-handed frame if you construct it as such. So the cross product is important, still an important aspect of how we're constructing things here. Probably an interesting question to stop and ask yourself for a moment is, what if you weren't doing this in R3, right? What if you were doing this in some larger context? What if you were, say, trying to fit a frame in some more abstract space, how would you come up with these, extra vector fields given the first two, right? What would take the place of the cross product? Is there, how does that play out? Well, I think that's probably one of the more interesting parts of this story of the frame field technique is, what takes the place of this idea in the more general context. Anyway, I don't have much to say about that except to say that it's interesting. So, the technique of the proof is sometimes useful to construct frame fields on a given surface. For example, the cylinder, x squared plus y squared equals r squared. So we can use the gradient to get a normal field, and then normalize it to get a unit normal, E3. And then, it's easy enough to see on the cylinder, right? Of course, you can see on the cylinder that with z-axis, right? It's pretty obvious that, U3 is like this, right? So it's clear enough that that is perpendicular to the normal to the cylinder. So, also just in terms of formulas, right? You can see that this and that are perpendicular. This also has length 1, so there you go. There's your second thing in the frame. And then again, we'll use that technique we just used in the proof, except this time we'll say E2 is E3 cross E1, all right? And it works out to, when you take this cross product, you get minus x over r u2 plus y over r u1. You can recognize that that's sine theta, that's minus cosine theta. In fact, that's exactly what I would call, here's what I would call it in terms of my multivariate name calling. If I was teaching vector calculus, I would call this z hat. I would call this theta hat. I would call this r hat. There is definitely something to be gained in teaching frame field techniques to calculus 3, but it's an uphill battle if you've not tried to do it before. But anyway, of course, frame fields have use in physics also, and this is a great notation for solving problems with cylindrical symmetry, for example, in physics, right? Anyway, if we do so construct the frame in this way, it automatically makes it a right-handed triple, because you may remember from our previous discussion of cross products back in the day that if I set up E2 as E3 cross E1, that automatically gives me the other cyclic permutations of this identity, like E1 cross E2 is E3 and E2 cross E3 is E1. Those come automatically once I set it up like that, given that the inputs E1 and E3 in this case are unit and they're orthogonal. Excuse me. All right, so our second example is the sphere, our old friend the sphere. There you go. I guess I should have done this example in green, I'm sorry. Oh well. So of course the first thing is take the gradient of the level function, normalize it, out pops this guy. And then a good example of a tangent vector field is the east wind. Is this thing always, if this is the z-axis, this is the thing that it's going like this way, I think, yeah. So in terms of multivariate calculus, this is really just theta hat. But anyway, more pragmatically, you can easily check that this is perpendicular to that, right? It's obvious that E1 dot E3 is 0 because you get like minus xy plus xy, so 0. And also, this is normalized to length 1, except at the north and south poles where x and y are both simultaneously 0, consequently giving us division by 0. All right. And then again, to get the third one, we take the cross product of E3 and with E1. Out pops this monstrosity. I'll spare you the details, but that's what it works out to. And you can check that in respect to my usual Calc 3 notation, this is in fact phi hat, whereas that is rho hat, and this is what I would usually call theta hat. So phi hat cross theta hat gives you rho hat. Anyway, in spherical coordinates, these are far prettier, but I will not digress further on that at the moment. Now, in order to make use, right, of the stuff we did back in Chapter 2, it's tempting to just do it directly, and in some sense that's what we'll do very shortly. But technically speaking, in Chapter 2 we were dealing with frame fields on either all of R3 or some sort of open subset of R3. So those are three-dimensional subsets, right? Now we're talking about this adapted frame field to a surface, right, which is a two-dimensional object, which of course doesn't match up with that setup. And there was a place or two where we actually did use the three-dimensional open sets to do certain arguments, right? And not too much, but it was there. And so how do you get to a three-dimensional open set from a surface? Well, you can look at what's called the ribbon, right? What you can do is just thicken, so to speak, the surface. What you do is like this. You imagine surface is like the blue, the M, and then you just kind of like continue it along the normal lines, or the normal vector field E3 in this case, plus or minus epsilon, and that gives you like a thickening of the surface. Give it a fuzzy edge, all of a sudden you got yourself like an open, genuine open set in R3, and there we can do, and you know, like we can steal the results we derived back in chapter 2, and then we can kind of like let epsilon go to 0, and we'll be able to maintain those results. Although I don't actually show you that analysis here, and I don't think really O'Neill does either. But it's intuitively clear that ought to work out. By the way, I think I saw this first in Shlomo Sternberg's great book on curvature. It's a Dover. I don't think I have it at the moment. A student has not returned it to me, but it's okay. All right, so I'll get it back when it's time. So connection equations on the surface then, basically, this is the theorem we had before. If E1, E2, and E3 is we didn't have the word adapted before, we just had a frame field, then the covariant derivative in the v direction of EI was equal to sum j equals 1 to 3 of omega ij, the connection forms acting on v, ejp. Now, adapted, right, means that E3 is serving as the unit normal. We'll talk more about that, but just to remind you, omega ij was the covariant derivative of EI in the v direction dotted with EJ. So if you really look at this, what this is just saying is that this is really just, in view of this notation, it's really not much more than just using an orthonormal expansion for the covariant derivative. So it's easy to get lost in what's actually being said here. I mean, half of this is really just notation and orthonormality. But anyway, it's worth taking a second to say what this means. Omega ij of v tells us the rate at which EI initially, I mean at the point P, right, rotates, in which EI rotates towards EJ as P moves in the v direction. Right. This, I think, becomes more clear as we do some more calculations, but so here's a proposition: the shape operator S at P for a vector v in the tangent space to P and M can be given by S of v is equal to omega 1,3 of v times E1 plus omega 2,3 of v times E2. And so that's, well, what was the shape operator? Well, so here we're taking the unit normal to be E3. The shape operator, remember, is the covariant derivative of u in the v direction with a minus outside. But that's the covariant derivative of E3 with a minus, right? But remember, the connection forms are antisymmetric. Omega ij is equal to minus omega ji. And if you just write this out, we've got omega 3,1 plus omega 3,2, right? Now omega 3,3 is 0 because omega 3,3 is equal to minus omega 3,3, which makes it 0. So we have these two non-trivial terms, and that's the claim, all right? So there it is, a formula for the shape operator in terms of these two connection coefficients. So you see omega 1,3 and omega 2,3 completely control the shape operator. They control the shape of the surface, so to speak. All right, and by the way, I used the flipping of 3,1 to 1,3 and 3,2 to 2,3 to absorb the minus up here. All right, no big deal. Come on, come on, come on. What else did we do? Well, we looked at coframes, right? And we used wedge products and exterior derivatives and some other things. So let's get back to that again. So we have E1, E2, E3 adapted to M. That means E1 and E2 are tangent to M, right? So, of course, the adapted frame, you could think about coframe, theta 1, theta 2, theta 3, but really only E1 and E2 are on the tangent space. They're really tangent vector fields. So it's only theta 1 and theta 2 forms that are on M. I guess you could say that theta 3 is also on M. It's just 0. I don't know, potato, whatever. The truth of the matter is, whatever you want to say, though, is that theta 3, it kills things that are linear combinations of E1 and E2. So for all intents and purposes, it's 0 on the on the tangent spaces to M. All right, and of course we have this duality as usual. So theta 1, theta 2, and I try to keep theta 1 and theta 2 upper indices, but I do slip up on that here and there. O'Neill has these indices down. As I mentioned before, to be consistent with other books which care more about locations of indices, it maybe should be the case that we write omega ij with one I down and one j up, or vice versa, depending on the convention. Again, I'm not getting into that, although I'm starting to get into that by writing these up. Anyway. Okay, so shockingly different books use different notation. So anyway, so omega 1, 2 gives how E1 rotates to E2, all right, and omega 1, 3 and omega 2, 3 capture the shape operator by E3, as this is revealed in pages to come. Nonsense, that was revealed in the last page. What a bunch of trash. Who wrote that? My goodness. Sorry. Sadness. All right, so an example. Dual to the cylindrical frame. So I have theta 1 was dr, theta 2 is rd theta, theta 3 is dz. If I look at r equals to r, that gives me theta 1 is 0, theta 2 is rd theta, and theta 3 is dz. Well, that's lovely, but now the theta 1 is identically 0, and the theta 3 is not, right? So the reason this happened is because my E3 wasn't the normal. My E1 was the normal. So there's a lot of this sort of notational, quicksand, or what do you want to call it? It's unfortunate, but oftentimes if we want to steal from our previous examples, we need to first relabel in order to get the third thing to be the normal. All right, not a big deal, but it will confuse you if you're not aware of it. All right, so let's look at a couple of examples then. So first of all, let's fix that cylinder one. So we just relabel it. Theta 1 is rd theta, theta 2 is dc, theta 3 is dr. So I just relabeled the order of the frame, all right? And so having done that, my theta 3 is identically 0 on the cylinder, r equal to r, and then I've got theta 1 is rd theta, and theta 2 is dz. There you go, there's the coframe to the cylinder. This is an adjusted version of example 2.7.6 of my notes, back when I was typing them, before I got busy. And who knows, maybe I'll come back to that sometime. So theta 1, theta 2, theta 3, I have adjusted example 2.77 in my notes to put the spherical one last, because that's going to be the normal one. Well, it's dual to the normal, right? Anyway, so excuse me, where's my purple? Purple, where is it? Oh, I got no purple. Oh well, red will do. So this arrow is, of course, rho equals to r. All right, in other words, take this coframe and adapt it to the sphere. When you do that, this thing collapses to 0, and you're left with these two. All right. Now, of course, these could be written in terms of Cartesian coordinates, but then they'd be ugly. All right, and all of that is also in my notes a little bit more. So Cartan's structure equations adapted to the surface are just kind of like what we saw before. You got the first structural equations, which of course we could write more elegantly as just d theta is equal to omega wedge theta if we wanted to, right? And we've got this one here, right? That is actually this is actually d theta 3, right, is equal to omega, let's see here, well, omega 3, 1, wedge theta 1 plus omega 3, 2, wedge theta 2, right? But this is 0, so this is actually the third. This here actually gives you this and that, all right? With the understanding that the third one's frozen out. And then you have Gauss's equation, right? And you got these guys from Gauss's equation is the first one, and then these so-called Codazzi equations, right? And these tell us how the shape changes from point to point. Remember, because we know omega 1, 3 and omega 2, 3 control the shape operator. And all right. So, and as I'm saying, they're really just the omega wedge theta and the omega is omega wedge omega equations, with this caveat that the third coframe is 0. All right. So here's an application. Sorry, I'm going to do it a little bit at a time. So, move it up a bit. So we have this spherical frame, r d phi and r sine phi d theta. I can calculate the exterior derivatives of theta 1 and theta 2. I get 0 and r cosine phi d phi wedge d theta respective. Of course, I also know that d theta 2 is omega 2, 1 wedge theta 1, right? But theta 1 is r d phi. So that gives me r cosine phi d phi wedge d theta, all right? That makes me think maybe, just maybe, omega 2, 1 is like minus cosine phi d theta, right? Now I can't be sure, because if there was a phi component, it would have been squashed because I wedge it right here, right? So this doesn't tell me that there is no phi component, but it does tell me that a good candidate for the theta component is just like minus cosine phi d theta, of course. Well, I don't know if you want to include the theta or not, but on the other hand, we have d theta 1 is equal to omega 1, 2 wedge d theta 2, right? But d theta 1 was 0, so 0 equals omega 1, 2 wedge r sine phi d theta. This right here kills any hope for there being a phi part of omega 2, 1, which is equal to minus omega 1, 2, which tells me that my guess before was in fact the totality of what we should have, minus cosine phi d theta, but then using antisymmetry of the form, I get omega 1, 2 is equal to cosine phi d theta. And there you have it. All right. All right. So this is based on example 2.77 of my notes, with the notation 1 going to 3, 2 going to 1, 3 going to 2. And if you look at the connection form I calculated there, omega 2, 3 is exactly this. However, I would caution you against trying to understand how my formulas are connected to O'Neill's, because they're a little bit different, and I'm tired of trying to figure out how they're different. Sufficient to say I've spent too long on that question. I refuse to look at it more. What I do know is that my equations for spherical things are consistent. So, all right, so the vector field form computations, now we're in section 6.2. There are three major results we need. Any vector field can be rewritten, can be expressed in this orthonormal expansion with respect to the adapted frame E1, E2, E3. Of course, only E1 and E2 figure into the expansion of tangent vectors. This is a tangent vector field, to be clear, right? One form on M can also be expanded in terms of the coframe, the dual frame E1 and E2, like this. And a two form, well, it's determined by its values on the pair E1, E2, like that, all right? So if you use these, you can calculate just about anything. So these claims follow, again, from the definitions we gave back in Chapter 4, as well as the duality of the coframe. Here's an example of how to prove one of these things. All right, so theta 1, theta 2 is a basis. Excuse me. So that means there has to be some C1 and C2. Now you could ask, how do you know it's a basis? Well, I don't want to get back into all that, but I gotta start somewhere. So let's just suppose we can see that that's a basis. This calculation actually may show it. Anyway, it's a set of, excuse me. Okay, so suppose alpha is C1 theta 1 plus C2 theta 2. I'm trying to show that C1 and C2 are just alpha of E1 and alpha of E2, but that's easy enough to see because if I let this one form act on E1, I get this expression right here, but duality makes that 1 and makes that 0, the dual basis condition. And likewise for alpha of E2, this is 0 and that's 1, so I get C1 and C2 respective. Consequently, alpha is as claimed. All right. And similar arguments based on dot products give you the first thing, and the definition of the two form back from chapter 3 gives you the third thing. All right. Something slightly more exciting. Omega 1,3 wedge omega 2,3 is the Gaussian curvature times theta 1 wedge theta 2. Hey, that's pretty cool. Now the Gaussian curvature is connected to wedge products of these coframes. And also the sum of wedge products gives me twice the mean curvature times theta 1 wedge theta 2. Excuse me. I wish I knew how to put this camera on pause. I just don't. Go get a drink. Oh well, the show must go on. Alright, so if I calculate this, right, using, oops, that's outside the frame. Sorry, using this idea, but with alpha equal to omega ij for appropriate omega ij down here, all right? So let's see here. Like omega 1,3 expands in the coframe like that, omega 2,3 expands in the coframe like that. You know, the first component, the second component, the first component, the second component, theta 1, theta 2, theta 1, theta 2. And when you take the wedge product, you notice like theta 1 wedge theta 1 0, theta 2 wedge theta 2 is 0. So you're just left with like 1 2 and 2 1, but 2 1 goes back to 1 2 and gives me a minus. So I've got this times that times minus that times that, and I'm arguing by the lemma, which I'll show on the next page, that that's exactly the determinant of the shape operator, which is somewhat believable, right? Because we had that formula before, which expressed the shape operator in terms of omega 1,3 and omega 2,3 without the omega 1,2. So like, there's hope for this before we do anything else. Just on that earlier formula we had. So anyway, that's the determinant of the shape operator. But of course, we know and love that and recognize that to be the Gaussian curvature times theta 1 wedge theta 2. All right, so let's prove that little determinant formula. Here it is. Determinant of S is omega 1,3 E1, omega 2,3 E2 minus omega 1,3 E2, omega 2,3 E1. So to find the matrix of the shape operator with respect to the adapted frame, the tangent part of the adapted frame, E1 and E2, I just have to look at S of E1 and see how it's expressed in terms of E1 and E2, and S of E2 and see how it's expressed in terms of E1 and E2, right? But since S of E1 is a vector, well, excuse me, using the using that formula I was just mentioning that we, I'll find it eventually. Where was that silly thing? Where did it go? Where was it? Where was it? Oh, come on. Was it page 4? Yeah, back on page 4, this guy. So this proposition back on page 4, which again was essentially just the definition, well, essentially just anti-symmetry of the connection coefficients and this theorem, right? So using this with V equals to E1 and E2, here you go. So S of E1 is omega 1,3 E1, E1 plus omega 2,3 E1 E2. So that gives me that the first column is omega 1,3 and omega 2,3 like that, all right? And then, likewise over here, I get omega 1,3 and omega 2,3, but this time with E2 from the second row, all right? So what's the determinant of this? It's exactly this times this minus that times that, which is precisely what we wanted, all right? Now, how do we prove 2? omega 1 3 wedge theta 2 plus omega 1 3 wedge theta 1 wedge omega 2 3. So it's a straightforward calculation, almost the same thing again. Well, it's not quite the same thing. I mean, we can use this matrix again for the second part, because after you calculate the wedge product and throw away things which are 0, you end up with omega 1 3 1 plus omega 2 3 2, but that's exactly this guy plus that guy, which is the trace of S, but of course we know that that's twice the mean curvature. So there you have it. Corollary, which is a very important corollary. I think this is called Gauss's, what is this? Oh yeah, he calls it the second structural equation. All right, probably warrants a label here. I need to get some white out, oh well. Second structural equation, all right, that's its name. D omega 1 2 is equal to minus the Gaussian curvature theta 1 wedge theta 2. Here's the proof. Gauss's equation was that d omega 1 2 is omega 1 3 wedge omega 3 2. But hey, we just learned that, of course, by antisymmetry, I can change 3 2 to 2 3, and then voila, that's exactly omega 1 3 wedge omega 2 3 was k theta 1 wedge theta 2 from the thing we just got done doing, part 1, right? So there you have it, the second structural equation. So a nice application of that, of course, is to calculate the curvature of the sphere. So here's your coframe, there's your wedge product, r squared sine phi d phi wedge d theta. I was permuting the order of this, but it doesn't really matter. I should just leave it alone, so I scratched it out. And on the other hand, I can calculate the exterior derivative of the 1-2 connection form. So I do that. D omega 1 2 is minus sine phi d phi wedge d theta. But hey, the second structural equation says that this has to be equal to minus k times that, right? So that gives me minus sine phi d phi d wedge d theta equals to minus k r squared sine phi wedge d phi wedge d theta. Of course, d phi wedge d theta is a non-zero 2 form, and so we can equate coefficient minus sine phi to minus r squared times k times sine phi. Of course, then the minus and the sine phi cancels, most places. I suppose ignoring those. Oh no, a spider. Spider. I think I'll let him live. So let's see here. Oh, so then that means that kr squared has to be equal to 1, which means then that k, of course, is equal to 1 over r squared. And there you have it. Calculation of the Gaussian curvature using exterior calculus. Principal frame field. So a principal frame field is kind of what it sounds like. It's a frame field which is adapted to the surface such that E1 and E2 are everywhere principal vectors. All right. So for non-umbilic points, this determines a particular choice of frame. Oh, up to a sign choice, right? Because you can always like take and like flip over to this. So if you've chose this frame field, right, I guess you can just kind of like do this, or you could also even use that one, right? There's a few choices because the principal curvature k of u is equal to k of minus u. So you know. Anyway, O'Neill points out that the surfaces of revolution, the tangents to meridians and parallels give you a principal frame, for example. Lemma 2.5, oops, sorry. Come on, behave. I'm trying to stay in frame here. Eee. My fingers won't work. Come on, fingers. Lemma 2.5. If P is a non-umbilic point of surface, then there exists a principal frame field on some neighborhood P of M. The argument goes something like this. If P is non-umbilic, that means, of course, K of U is non-constant at P, right? Which means that the principal curvatures are not equal, but that means the difference is non-zero, but by continuity there has to be some neighborhood, in which the principal curvatures are not equal, right? And then O'Neill makes some argument that simultaneously normalizes eigenvectors of S in a neighborhood of the given frame. If you want to see the details, they're on page 271 and 272. Something sneaky in that argument. But anyway, moving along here. So, alright. So let E1, E2, and E3 be a principal frame field. So that means that there exists functions K1 and K2 such that the shape operator on E1 is K1, E1, and the shape operator on E2 is K2, E2, right? But what does that mean about the coframe? And what does that mean about, well, the shape operator? Well, I guess nothing more to say about shape operator. I guess that's that. But if you look then at the shape operator E1 in terms of the, again, going back to that page 4 proposition we had, I can expand the shape operator in terms of the 1-3 and 2-3 connection forms. And on the flip side, of course, I can write K1, E1 plus 0 times E2, right? Just use your imagination. There's 0 times E2 there. Linear independence of the adapted frame, though, tells me that what's underlined in red has to be equal, what's underlined once in blue has to be equal, and likewise for S of E2, the double underline in blue has to match the double underline in blue, and likewise for the double underline in red. And so there you have it. We have then derived that omega 1, 3, 1 is K1, omega 1, 3, 2 is 0, omega 2, 3, 1 is 0, omega 2, 3, 2 is K2. But that implies, of course, since these are the 1 and 2 components of the form, the 1 form omega 1, 3, and these are the 1 and 2 components of the 1 form omega 2, 3, we can read from these 4 conditions simply that omega 1, 3 is K, the first dual form, and omega 2, 3 is K2, the second dual form, the second coframe. And then there's this snazzy little theorem that you can derive from this. If E1, E2, E3 is a principal frame on M, then the E1 acting on the second curvature function is the difference of the normal curvatures, K1 minus K2, times the omega 1, 2 of E2. And the this, by the way, this is the change of K1 in the E2 direction, right? That's what that is. And so the change of K1 in the E2 direction is governed by the omega 1, 2 acting on E1 and the difference between the principal curvatures at that point. So this makes good on that claim that we made earlier that omega 1, 2 tells you how the, maybe I didn't make this claim before, but I should. Omega 1, 2 tells you something about how E1 and E2 are rotating into each other, right? In this case, that's linked to the changes in the principal curvatures. So it's kind of more special, but all right. Anyway, so to prove that theorem, it's really, really nice. A little calculation. So omega 1, 3, remember we just learned was K1 theta 1, and omega 2, 3 we just learned was K2 theta 2, so you plug those in, you calculate the exterior derivative, all right, and then you bring stuff, just pull out the constants, all right, and and we also use the d theta 1 was omega 1, 2 wedge theta 2, right, and then you bring all the omega 1, 2 stuff to one side, like that. So dk1 wedge theta 1 is k2 minus k1 omega 1, 2 wedge theta 2, great. And then what I do, now O'Neill says he lets it act on E1 and E2, and that's fine, but I prefer to use the expansion of these one forms like dk into its components. Like, so dk1, for example, I just wrote this piece of it, right? But really dk1 would be like, it's dk1 acting on E1 theta 1 plus dk1 acting on E2 theta 2, right? That's the full story. But I just wrote that piece up there because I knew that I don't even need to write down this theta 1 piece because I'm going to take the wedge product with theta 1, right? And because I'm going to take the wedge product with theta 1, well, I already know, it's going to die in this calculation. So like I already know that this piece is just going to vanish when I put it up here, so that's why I didn't write it. Now, as to confuse the students, I did write it over here. So like omega 1, 2 is omega 1, 2, E1, theta 1, plus omega 1, 2, E2, theta 2. This is the expansion of this one form in terms of the coframe, right? But of course I didn't really need to write this because I know that omega 2 wedge, theta 2 wedge, theta 2 rather, is trivial, it's 0, and so I'm just left with this piece, right? So put it all together, and so change theta 1, theta wedge, theta 2 to, you know, from theta 2 wedge, theta 1, that brings the minus out, and so it gives us this lovely equation. Turn the page. Comparing coefficients on the theta 1 wedge theta 2 yields this lovely equation, which of course dk1 E2 is E2 acting on k1, going back to our meaning of differential and vector fields acting on functions. And there you have it. And the form, and so, you know, here I wrote down the argument for the other one, which is the same argument again. I won't go through it. See, this theorem shows that the principal frame omega 1, 2 controls how the principal curvatures k1 and k2 change in the principal directions E1 and E2. But here, I gave you this if you want to look at the other case, which O'Neill doesn't have. I just wrote it out for kicks. Anyway, that will conclude this lecture, which is lecture, what lecture are we on? Lecture 18. The next lecture 19 will be on so-called global theorems. And anyway, there are tons of great homeworks in this chapter. I hope you do them. I did a bunch of them. I think about 30 pages of homework I have posted on chapter 6 of O'Neill, so you can hopefully make use of some of my work there, and maybe do some other problems. Whatever it takes for you to understand this is what you should do. Thanks.